topos, if you know what toposes are. And so we'll talk about a topos theoretic view of dynamical systems, but for a pretty specific, well, I don't know if I could say real world, but for an actual kind of real world use case, which is the national airspace system in the US. So I'll talk about that, and I'll talk about relations in a topos and what that kind of means. And then I'll give a motivation and plan, and then I'll talk about the actual story. So the example system to have in mind for this whole thing is where there's dynamical systems everywhere. And by dynamical system, I mean something that has behavior, something that does something. So I'm a dynamical system, my airplane's a dynamical system, etc. So dynamical systems are all over the national airspace, and in something called the Next Gen program at NASA, they want to double the number of airplanes in the sky for some reason. Maybe drones, or I don't know. But they want to remain extremely safe, which means they hope to have one problem in every billion hours of flight. So that's the kind of goal that these are. And one main thing you want to keep safe is safe separation. So you want your planes to be safely separated from each other. But you might think that's pretty easy, you just kind of avoid each other. But if you ever walk next to someone on the street and kind of not know which way to go, and you both go left, you both go right, well, if you can't stop, then that's really bad. And you can't communicate directly. They can't necessarily see each other. So they use a system of radars, pilots, ground control, radios, and collision avoidance systems called TCAS. So those are onboard collision avoidance systems to negotiate and figure out how they're going to avoid each other. And all of these are dynamical systems in some large enough sense, meaning they're all behaving something. They're all doing something according to some contract or some rules. So we have what people sometimes call a system of systems, which is the reason they call it that is because the designers of the various systems and the modelers are not using the same language. So one person is using labeled transition systems, which are like finite state automata or infinite state automata that are moving around. Other people are thinking in terms of differential equations. So you have all sorts of different people thinking about how these machines are operating, and then they come together to work in concert to solve the problem. So this is an issue where lots of different models are coming together. Here's a little picture for one thing that could happen. So in this picture, there's a fixed system involved where we have two planes only and a radar satellite. And the radar satellite is the two planes are sending their altitudes up to the radar satellite just passively. And the radar satellite is sending back down both altitudes of both planes. And each plane is sending each other its plans, what its collision avoidance system is telling it to do. So plane 1's collision avoidance system is saying, go up. So it's telling plane 2, I plan to go up, and vice versa. So this is what they're doing. And then you could zoom into plane 1, and plane 1 has two incoming things and two outgoing things. So you see two incoming and two outgoing. This is kind of that operatic perspective, but it's just morphisms in a hypergraph category. Whether you like one word or the other word. What I mean here is that I'm going to plug this box into plane 1. And when their TCAS comes in, their collision avoidance plan, my TCAS system takes that together with the radar signal and communicates something both to the pilot and to the outside world, to them. And the pilot, maybe it's a very stupid pilot whose only job is to delay for 3 seconds and then do whatever the TCAS says, or maybe it's got some psychology and it actually makes decisions based on other things. But in this model, it's just going to be a delay. So it delays, so now you have this labeled transition system or something barking commands whenever it wants to, move left, move right. And then the pilot is doing what it says a few seconds later, sending that information to the jets and the wings to change their shape and to go faster or slower, and that affects the altitude. Okay, so these pictures here where there's wires with arrows, that kind of indicates the direction of signal passing. Okay. Whereas many people like to think about dropping the arrows and think about just variable sharing. But whether you like that or not, it's the same picture. And the planes, the way you should think of each of these things, plane 1, plane 2, and plane 3, are constraints on the types of behaviors that can occur on their wires. So an airplane is a constraint a well-working airplane, say, is a constraint that says, if I receive these signals, I promise to act this way. And that's actually what I am too. So if you send me some force signals, I promise to act by my mass. And if you send me some information about someone's in trouble, I promise to run there with amazing speed. And so I have all these constraints and morality or whatever it is that guides my behavior. But what that means is that there's some relationship between what I see and what I do. And that's what a system in some sense is to me. So you can challenge that later, but that's what I'm saying the system is some constraints on behavior. So if I know you're close to me, I'll move up. That can be a constraint. So these pictures, formally, if you want, they could be composition diagrams in a hypergraph category, if you like those words. But these, by the way, in a real system, these wires are constantly changing. Like which planes are interacting is changing all the time. And so if you're interested in that, you can ask me at the end also how you can model that kind of thing, where you don't know who's going to be affected to who. But in a fixed snapshot, you might see this picture, and then you're in a hypergraph category setup. And what a hypergraph category, one thing it can do if it's kind of, one type of hypergraph category is that of relations. So you could think that each wire is a set, and each box is a relation. That's not going to get us very far in this picture, but that's an example of a hypergraph category, where a relation is a constraint on what A1 through AN tuples would count as being in a relation. So relations form a hypergraph category in any topos. There's a notion of relation. So in the topos of sets, these are what I said before. They're kind of subsets of a product. But in an arbitrary topos, you have something called a subobject classifier, and a relation, kind of variable relation, varying in time or space or whatever your topos is about, is a function from that product type to the subobject classifier. In sets, the subobject classifier is 0, 1 to Booleans, and so a subset is just a yes/no question you ask a set A. Is it good or not? Yes, no. But in toposes, the kind of truth values you have are not just yes, no, it's more like when. So if I say it's raining, then you don't say yes or no, you say it's raining in Lausanne or it's raining in Boston. So you give the where of where it's raining on the topos of the Earth, not yes or no. Yes would be replaced by everywhere it's raining everywhere. That sounds bad. And it's raining nowhere would be false. That sounds bad. But most of the time it's something in between. So the question for this talk is, what's the topos we need for the National Airspace System? In other words, what's a topos that's general enough to accommodate delays, differential equations, label transition systems, things that act stochastically through time, or with differential equations, or with things that are time dependent in a different way. So where do all these behaviors live? And the answer is that they live in time. So everything I'm doing is something that happens in time. Even my thoughts, there might be a function from thoughts to brain activity or from brain activity to thoughts, but the sheaf or whatever kind of thing I want my thoughts to be in might not exist in space necessarily, but for me at least they seem to exist in time. And all behaviors are things that happen over time, at least here in this talk. So the major guide for our work was, because we didn't know how to make a topos that would accommodate all dynamical systems or everything we'd ever want to do with behavior. But if it can accommodate this national airspace example, then it's kind of rich enough, we thought. And so we wanted, there's lots of different logics, temporal logics, logics for label transition systems and differential equations. There's lots of ways that people have for putting these together with themselves, but not with each other. So we wanted a big tent formalism. I forgot to say who we is. We is me, Patrick, and Christina. So the logic stuff is me and Patrick, but the kind of stuff I'm talking about now is with Christina. So we need to combine many different frameworks into a big tent, and that includes differential equations and continuous dynamical systems, finite state automata or label transition system or infinite state automata, things that happen at discrete times or whatever they want, and things that have non-instantaneous rules, which I'll talk more about later, but like delays. We need a logic in which to prove the safety of a combined system. And what that means is that, what I'm saying that is that national airspace people, a lot of them work in something called formal methods. Formal methods means actual proofs with for all and exists and or and not. where you write a proof that your system is safe or that it's not going to have some kind of Byzantine, I don't know, some kind of error that where there's someone lying and you don't know what to do about it, so you need at least 2 times as many truth tellers or something like that. So they need a logic to prove those things, and they have those logics for each of these specialized components, the label transition systems or linear temporal logic or dynamical systems. And we need a logic where you can combine all of them in the end. So you have all these systems, and now you finally put them together somewhere and prove something. Because that doesn't exist right now. So the relationship to toposes, how this is related, is that toposes have an internal language and logic built in. So if you could find the right topos for thinking about these things, you could just extract some of or all of the internal logic and start working with that. And you could use it directly in a proof assistant, as long as that proof assistant does constructive logic, to prove properties of the national airspace system.
But why would you want to use constructive logic in this aspect?
Right, because maybe the topos is not Boolean.
Yeah, but I mean, do you know in advance that you want classical or constructive logic?
Well, so classical logic is intuitionist logic or constructive logic plus an extra axiom. And the question is, do you want that axiom to hold or not? And so in our case, it does not hold.
But do you want it?
I don't want it. So if you fix any moment of time, like right now, it holds. But if you look over longer intervals, it doesn't hold. So Boolean logic is for one snapshot of time. Is it raining? If you're right now, you can answer yes, no. If you're right here and right now, you can answer yes, no. But if you're in something larger, you often can't. So we're going to talk next about the Toposes behavior types, which is, that's the name we gave it. So how we chose that topos, something called the interval domain, which is pretty close to that topos, and translation invariance, which is what's called a quotient topos. Okay, so toposes were invented by Grothendieck, and they generalize topological spaces. And so the basic idea of toposes is that instead of, it tells you what can live on a space rather than what that space is, in some sense. So the space, like Earth, isn't the interesting thing. The interesting thing is what happens on Earth. So the space is just the habitat or site, we call it site, where stuff appears. And the stuff is what we care about, and that's what the topos is about. So the definition of topos, which you won't understand because I just defined it in terms of something else, unless you already know. A topos is the category of sheaves on some site. So if you have a site like the Earth or a topological space, you get a topos. So 2 examples, topological spaces and databases. Any topological space, like the surface of the Earth, defines a site. And the things that live on the Earth are vector fields and scalar fields and any sort of bundle. But for example, our behavior, I guess, would live on the Earth, maybe plus time. So, but any kind of bundle, any kind of other space, it maps to that other space. There's lots of stuff that lives there, but you can kind of think of it as like vector fields. Another very different kind of example is if you have a database schema S, which just means how your tables are going to be laid out, then the instances, which means filling them with data, are what you actually care about. The site is what the table layout is. The stuff and what's happening there is the data itself. And all the various database states or instances on that schema would be the topos. So the question here is, what's a good site at which behaviors live? Because we're interested in what lives there. And the site is going to be basically supposed to act like time.
Can any category be a site?
Yes, any category can be a site, but you have to add an extra ingredient, which is the coverage. If you don't add one, then you're saying, I'll take the trivial coverage. So any category can be a site. So a first guess for time, if you believe that time is a good place to put behaviors, is that you should use the real line. So what would a behavior type be if that's what you chose? The answer is that you would need to tell me for every interval in the real line, like 0, 10, all the behaviors, a set B of all the behaviors that can live on that interval. So what are all the behaviors that can live there? And for every subset of that interval of time, so over the course of 9:30 to 10:30, what are all the possible David behaviors there are that I would consider within the realm of me. That would be B of 930 to 1030. But now if you take any slice of, any piece of that, so from say 950 to 955, you can restrict my long behavior and tell me what I'm doing over that subinterval. So there's a way to restrict my, any movie to a sub-frame in that movie, sub-time window of that movie. And of course, if you restrict to 950 to 955 and then restrict again, it's the same thing, just restricting all at once. But more importantly, there's gluing conditions, and I can break them into two pieces. One is what I call continuity, and the reason I'm breaking it into two pieces like this, what you really want to say is that for any open cover of one open set by others, there's some kind of gluing condition. But I'm going to break it into two because I'm going to keep one of them in what goes on from here and discard one of them. So continuity says that if you look at what I can do between 930 and 1030, and then you look at 931 to 1029, 930 and 30 seconds to 1029 and 30 seconds, and you do expanding windows, then what I can do over the big window, 930 to 1030, is the limit of these other ones. And composition gluing says that if you have one section over one time interval, and you have a section over another time interval, and they agree on the overlaps, then you can extend it to the whole time interval.
It looks like you're taking a full back.
Yeah, full back. I'm supposed to pull that.
I expected it to be a push-up, so you're talking about gluing little pieces.
Oh, so in the topological space, it's a push-out, so that's right. So in the topological space, I have like this, and I have their union. But then a sheaf is contravariant, and so you ask that this be a pullback. So a behavior over here is a pair, a behavior here and a behavior here that agree.
Right.
But I can give two reasons why not to use sheaves on R as the topos. One is that I want behavior types to be, the most important is I want non-composable behaviors. And so here's two examples. One is what I call roughly monotonic. So imagine a function that is roughly monotonic. So for any interval of 5 seconds or more, you can see it's gone up, but it's allowed to go down a little bit. So it's allowed to go down, but if you look at least 5 second intervals, you'll see it's always going up. That's something that doesn't satisfy the gluing condition, because you could have something that's going down for 4 seconds and say good. Something that's going down for 4 more seconds and say good. They agree on overlap, so good. But you don't get something that satisfies for the long 8 second interval. It goes down for 8 whole seconds, that's bad. Or what's called bounded. On that one, though, you could still check on 5 second intervals and you'd be fine. But bounded distance says that for all pairs of times, my function at these two times is between, the difference is between -5 and 5. So I'm always kind of on a pivot foot and I'm never allowed to leave more than a certain distance. That's something you could check. Oh, I'm fine here, and I'm fine here, but on the glued thing it doesn't work. So we don't want composition gluing. Basically, the idea is you want to, in sheaves on R, you can measure everything at tiny little epsilon intervals, and everything's determined by that. Which means if something is compliant with some contract, like over just tiny intervals of time, it'll be compliant for the whole thing. And that's fine for like rain. If it's raining now and it's raining then, it'll be raining the whole time. But if you look at things like, if you give me a red stone, I'll give you back a blue stone within 5 seconds. And if you look at the first, which is a very important thing to do in national airspace, they're giving each other stones all the time. So if you look at the first 4 seconds, you see me give a red stone. You don't see anything happen, but there's no violation because I have 5 seconds to do it. And if you look at the last few seconds, you don't see me hand the red stone, and you don't see you do anything either. And so it also looks compliant. But if you look at the long interval, you see non-compliance. So when you want to be able to talk about things over extended intervals, not just very local intervals of time, you need to drop the composition gluing. And the other reason not to use sheaves on R is that we want to be able to compare behaviors across different time windows. So for example, a delay is somehow the same behavior at different times, whereas sheaves on R sees no relationship between 0, 3, and 2, 5. It doesn't understand that those are kind of the same amount of time. So if you want to be able to compare things over different amounts of time, what we're going to do is replace intervals by their duration. So, or their extent. So this is what we call translation invariance. And so we're going to discard composition gluing and add translation invariance. So to discard composition gluing, you get something called the interval domain. And domains are a popular, kind of a popular part of topology, something called domain theory, and Sampson wrote a book on it. And so the category we're going to use is the closed set of intervals in the real line, just like before. But the coverage we'll use is only that first kind of continuity coverage. That what I can do over 930, 1030 is the limit of what I can do as I grow to it. So the interval domain is not Hausdorff, but it's called sober, which is a nice condition. The points of the interval domain are intervals, du. So D for down and U for up. That's a point. This is a point, this is a point, that's a point. And an open set is an open interval AB, just like before, but now AB, what points are in? Well, all closed intervals inside of AB. So that's the interval domain. This is called the stop topology. And there's a specialization on order on points, which says that one interval could be less precise than another interval. So it's kind of a weird order that I don't like so much, but it is the usual order. And the Scott domain, I'm on the interval domain, and it says that this one is less precise than this one. Okay, so we're going to visualize the interval domain using the upper half plane. And so the upper half plane is a set of all points x, y, where y is bigger than or equal to 0, as you probably know. But it's better to use midpoint and radius. So I'm going to use the upper half plane is a set of midpoint radiuses. It's just, this is the x, that's the y, but it's just, I'm writing it a different way because there's a continuous bijection between the upper half plane and the interval domain. And basically, you take an interval and you replace it by the point in the upper half plane that's at its midpoint and at a height of its radius. So now every point in the upper half plane counts as an interval. That counts as this interval. So there's a bijection between the upper half plane and the interval domain, but the upper half plane has more open sets. In the upper half plane, this would be an open set, whereas in the interval domain, you get something interesting. The open sets are what's called the one Lipschitz functions. So that's an open set. Everything down here consists of one open set. So it's all the intervals that are under this line there. This Lipschitz function corresponds to all the intervals inside of it, that midpoint radius trig. So one Lipschitz functions show up here, and if you're one of those people who likes the Catalan numbers, then these are kind of a version of the Catalan, continuous version of the Catalan numbers. So anyone who likes Catalan numbers should talk to me about that. Because I've grown very fond of them since this. So, right. So we want to be able to compare behaviors from different time windows, and that's the second thing I want to build in. So we want to say that a delay is the same behavior at different times. And the way we do this is we consider a translation action of the group of real numbers on the interval. So I have an interval, 0, 5. I have a number like -12. I get -12, -7 as a translation of that interval by that real number. So this is a group, the real numbers, and it acts on the interval domain. That's a continuous action. And so I wanted to find IR mod triangle to be the localization of IR by this action, which just means I add all sorts of isomorphisms. It says that 0, 5 is the same thing as -12, -7. 0, 5 is the same thing as 1, 6. I add isomorphisms to my site that make it impossible to tell where that interval started and ended. And then and if you're worried and think, no, I want that, I want to know where it started and ended, then we'll get it back later, so don't worry about it. And so IR mod triangle, which is the actions, is what I'll call the site of translation invariant intervals. But and we're going to get a quotient topos, so the Sheaves on the interval domain. So, but there's a skeleton of this that's easier to understand. So the skeleton of this category here is the following site. So a site always has a category, and the category here is just the set of non-negative real numbers. And the morphisms between two objects, so if L prime is an object and L is an object, I think of them as like the interval 0L. And a way of a morphism from 0L into 0L prime into 0L is just a decision about how far on the left and how far on the right, R and S, to put this interval here. I don't think this diagram is very good, but basically I'm putting R on the left, S on the right, and so R plus L prime plus S equals L. And those compose in kind of obvious way when you write it down. So the coverage is that when you look at all the L primes that are quote unquote way below, which people write the wavy arrow here, L, which means if you look at things that are where R and S are allowed to be greater than 0, but they're kind of approaching L, that's a coverage for this thing. That's telling you what kind of co-limits you want to become limits in your sheaf, in the category sheaf. So a sheaf, what is a sheaf? Whenever you have a site, you can define sheaves. And so a sheaf on this site assigns what we'll call a set of possible behaviors to each length interval. So we'll get a restriction map for every subinterval. And so there are certain things I can do over an interval of time, over 10-second interval. And if you look at any subinterval of that, you can restrict. So the way we're going to get back the old topos IR, sheaves on the interval domain, is by finding a certain sheaf in B. B is a sheaves on this guy, so a certain object in sheaves here. And it's the behavior type of a perfect clock. And it says that what it's allowed to do over an interval L, say 5, of time, is all clock runnings for a 5-second interval. So if you look at your clock for 5 seconds, you just found one section of time, okay, 5. But if I look at my clock right now, I also get one. And all possible ones are time. Behavior of a clock over a duration of time. Right. So that's the topos we'll be using. And so we'll find, I guess I'll say this, I don't know if I say this in here. Sheaves on the interval domain is the same, is isomorphic to sheaves on this IR mod triangle, which is called B, when you slice over time. So this is called an étendue. It's a type of topos, and étendue means extent in French. And the reason is this is kind of intervals of time where these are kinds of extents of time. They're not placed anywhere, they're just the extents.
Is B just that sheaf category, or
Yeah.
is that whole slice? Okay.
Well, now I've ruined it.
Yeah. See what you mean.
Yeah. So now I'm going to talk about type theory because this is trying to get us towards the logic. Toposes have what's called an internal logic. So these aren't necessarily what you want because you can't program them into Coq or Lean or some kind of automated ecosystem because you can't axiomatize it. It's too big. So what you want to do instead is find a small portion of it called type theory that you invent that with some, which I'll talk about now, that kind of has semantics in that topos. So you've got this, suppose you agreed and we talked about it and you finally agreed that, all right, I think this topos seems pretty good for talking about behaviors. Then you still want to get a logic out of it, and what you're going to use is a type theory for this topos. So type theory is useful, very useful in computer science, and what I think, and I don't know anything about it, if you want to ask someone about it, ask Bart about it. He wrote a book about it. So it's basically a bunch of language rules from my point of view. For example, you might have a type theory called the simply typed lambda calculus with some types and quotient types, and that's your type theory. But in any type theory, you start with some atomic types and terms, or any type theory I know about. So take all this with a grain of salt. You start with atomic types, terms, and predicates, and you build new types, terms, and predicates using constructors. So the types, maybe I give you for free the natural numbers, which is called a natural number object. It's a place where you can do induction, kind of. You can ask me about that later. And I give you a type called prop, which is all the kinds of propositions you're allowed to have, not just true and false, but where or when something is true. But you don't tell me what it means. You just give me this language, the natural numbers, prop. And you give me a way to construct products, exponential objects, sums, quotients of any type you've already given me. So you just say, oh, given two types, here's the symbol for the product type. And then you give terms like tupling. So if I've got a type A in my type system and type B, then I can form a product type A times B. And now given a term of type A and a term of type B, I can construct a term of type A times B, and that's called tupling, where I can get projection, lambda abstraction. And then take predicates and hit them with exists and for all, and or not implies true, false. And you're allowed to kind of take predicates like it is raining and it is sunny and ask, is it raining or sunny? And then finally you add axioms, which are logical statements. So it's all just language rules of how you're allowed to build terms and types and proofs and all sorts of things in this world. And I have to admit that I always thought this was really boring, and that you should always just look at this from category theory point of view, and that this type theory stuff was just trying to be category theory, and it wasn't. But then I was wrong, because it turned out to be really cool from my point of view when I saw the cryptQL semantics for it, and initial benefit language for topos. So what happens is you start with these atomic types and terms from your topos. So you give each atomic type a meaning as an object in your topos, a sheaf. So the types are going to turn into sheaves, the terms are going to turn into sheaf morphisms, and the axioms are going to be facts about commutative diagrams and other things in your topos. Limits and colimits and quotients and all sorts of stuff in your topos. We're going to be able to encode that in logic rules. And then the cryptQL semantics is a machine that turns any logic you write down. Like you write down for all x, there exists a y, such that f of y equals x, which says that something's surjective. And you start writing down, if you want to make a proof, you say take an x, let y equal, whatever, and you write down a proof like this. And the cryptQL semantics takes this expression and turns it into a fact about toposes. And it takes your proof and turns it into a topos proof. And that topos proof automates so much of what's going on in your topos. So for example, all these are facts about sheaves. And what for all x means is for all sections and all restriction maps, if you take an object if you take an element of some size and then you restrict it and you ask questions. So this for all turns into for all restriction maps. Exists turns into there exists a covering family and a section X in each element of that covering family. And all sorts of stuff that happens in the topos is being encoded by just these language rules. And when you write down this take an X and let Y equal and stuff that you think you're acting set theoretically, this is translating it into all sorts of things about taking covering families and restriction maps and all the various things that are going on for sheaves. Each connective means something in that sheafy world. So the statements, this statement and this proof of it, both of them would be kind of recursive structures where you peel off pieces. For all restriction maps, there exists a coverage such that blah blah blah, and the cryptQL semantic kind of recurses over that construction. So it does a lot of the heavy lifting. You write a proof here, and you don't need to understand what that says theoretically, but you can always decode it and see. So, for example, in the type theory of a topos, where you have a natural numbers object, you can define what are called the real numbers in that type theory. And you follow Dedekind and say that a real is two subsets of the rationals that come very close to each other. So you say it's two propositions on Q, two predicates on Q, something called down, and this is a delta, and that's an epsilon, or down, up. So it says these are going to be lower bounds. Any Q that satisfies this predicate here will be a lower bound, and any Q that satisfies this predicate will be an upper bound. But remember, you don't satisfy things yes or no, you satisfy things where. So it says whenever, this is telling you where we have, or when we have a lower bound, or when we have a upper bound. And so there's some rules that Dedekind wrote down, but you can encode them all in this internal logic. You can encode them all in logic. He could have done this. But if you do it, these axioms here, it works well. Sorry, the Joyal crypty semantics turns it into something that's meaningful and nice. So this says one thing about real numbers is that if you have a lower bound, if q is a lower bound for a real number, like 3 is a lower bound for pi, that's the case if and only if there's some bigger real number that's also a lower bound. 3.1. If 3.1 is, then 3 is, and if 3 is, then there's something bigger. So if you write down these things and then translate them into cryptic-Joyal semantics, you might get nonsense, but it turns out over and over that you're satisfied with what the cryptic-Joyal semantics gives you. It just works well. So it turns out that if you are looking at the topos of Sheaves on a topological space, then this type that you build with the cryptic-Joyal semantics and Dedekind type turns into the usual sheaf of continuous real value functions. So the usual topological space of real numbers, for any other topological space, you can ask, what am I mapped into? And those form a sheaf. And that sheaf is exactly what you get by just writing down the Dedekind's 1900s axioms for whatever it was, for real numbers.
David?
Yeah.
I mean, I agree this is extremely nice, but you're explaining that this is what converted you to type theory, right?
Yeah.
But, I mean, would you call the cryptic-Joyal semantics type theory?
I guess it's, I don't know. I guess it's a place where you can incorporate type theoretic statements in the topos. Okay. And so that converted me to liking working with type theory. Okay. So ask Tom later why there's some caveats in what I'm saying. If he thinks there are. Or I don't know.
I mean, carry on.
There you go. So we can drop some of these axioms to get other interesting numeric objects. So if you drop bounded, you can get unbounded real numbers, plus or minus infinity. Or you can drop located, which is one I kind of grayed out here. And that way you don't force your intervals to get extremely close around pi. You allow them to be separated, and that allows you to look at intervals. So we can get the interval domain internally or externally. So in the type theory that we'll use for this topos, we just add one atomic type, and you don't even really need to do that, but we add one atomic type called time, and it's a subset of the type of interval reals. So as you might remember, time was kind of interval of time over any length. And time is an R coarser, which means that if you have a real number in time, you can translate perfect behavior on the clock. You can translate that behavior by a real number. If you have 2 times, you can subtract them and see what difference. You have Dock's clock in Back to the Future and Einstein's clock in Back to the Future, and they're both exactly on with each other, but there's just a 1 minute difference or something. I don't know if you've seen that movie, but that happens at some point. So with this type, you can make temporal logical statements like I did in the beginning. It says that something is roughly non-atomic for all T1 and T2. If T1 plus 5 is less or equal to T2, then F of T1. We already have, from what I've already shown you, this already makes sense. And it's a logical statement, and if you unwind it in the cryptic-Joyal semantics, you look at some sheafy stuff and see a function of time of a real variable that satisfies this, what you want it to satisfy.
A little bit of trouble type checking the time as a subset of IR.
Yeah.
So it was a free sheet.
Oh yeah, time's a sheaf. Everything in here is a sheaf. Yep. And IR is a sheaf. Oh, that might have been. So here I wrote. So IR is the type or the of all pairs of predicates on the rationals that satisfy bounded, rounded, and disjoint. That's not located. And I know you can't parse that fast enough, but it is there and we can talk about it. And it just says that time, when you ask for a time of length, time of length L is a set of all kind of like the set of all du. Oh, it is the set of all du, where u minus d is L. And the point is that you kind of get a real interval with some properties.
IR is a sheet in one category. And sheet of
For any topos, there's something called IR.
Oh,
And it always is these axes.
okay.
Minus the last one.
I was confused because earlier you were talking about
I
this
know.
category. of
Yeah, so we
sheets
put
over IR.
IR back inside. It re-entered its own category somehow. So we have IR externally, and that's where my topos kind of lives, or a portion of it. But it's also something you can define internally, and we'll get all mapped to it.
Just the Dedekind reals.
The Dedekind reals is all that.
Which you can define in any topos. And
Yeah, you
in
can
other
define
toposes it might look completely different.
Yes.
But it's weaker than the Dedekind reals, right? Because you said you dropped some.
Yeah. Yeah, right. The Dedekind reals you can define in any topos. You drop one axiom, you get the interval reals.
But you both want to be in the topos for sheets over
It
IR
turns out that
and look
yeah.
at this object in IR.
Yeah.
In itself.
In itself, yeah. Right, because we use that to define time with one. Yeah, time is a subtype of that. So now, I'll just talk about subtoposes. Oh my goodness. 36. Okay, sorry. Okay. So we refer to Levier-Turning topologies, if you know what one basically is, as a modality, because we're working kind of type theoretically or logically, and we're working kind of temporal logically, so modalities are something people talk about in that context. But what is one? It's a function from prop to prop where it satisfies three rules. P implies J of P, so it's kind of a closure operator on prop. P implies J of P. J of P implies J of P, and either of the following two conditions, that J commutes with and, or that J is monotonic.
Is prop a sub-object classifier?
Yes, prop is a sub-object classifier. It's the type of propositions, or externally we call it a sub-object classifier. So for any type U of prop, maybe U is a proposition, it's raining. Then there's a new, for any P, I can convert that to a different proposition. So David is happy or something. The proposition David is happy implies that if it's raining, David is happy. And all of these three conditions are satisfied for. If it's raining, then blah. That's a J. Or it's either raining or blah is another J. That's a modality. Or if P, then it's if P implies it's raining, then it's raining. I mean that sounds, I don't know what it sounds like you're saying that for emphasis or something. If P says it's raining, then it's raining. But this is called the quasi-closed modality. And for example, if you use U equals false, you get P implies false, which means not P, and then you say not P. So not is a modality in topos. So these are kind of three important modalities, but there's lots more. But these are the ones we'll need here. So time is not zero. It somehow picks out the point time equals 0. And when you look at the topos of Sheaves, for any type of modality, you get a subtopos of Sheaves, and it's an internal copy set. So their logic is Boolean. So as I was saying to Mark earlier, if you fix 1 second of time, 1 moment, infinitesimal moment of time, you get a copy of Boolean logic. But it's kind of a skyscraper sheet. But most of the time, the logic is not Boolean. So another thing you could say is, if you've witnessed the moment 0, then T is true. So that says either T is apart from 0, you didn't witness 0, or P is true. This is a modality we use, kind of like witnessing 0 times 0. Another one is that intervals of long length don't matter. All that matters is that for all time, when you look at instant 0, P is true. That's a modality. That way we embed the real line into IR. So IR is kind of the upper half plane. The real line is the intervals of length 0, and we can embed the real line into the upper half plane or into this sheet into this topos using this modality. I for point-wise. Okay. So from here we can define internally the derivative of a real value function. So if you take the internal variable reals, which means point-wise reals, which means kind of a copy, maybe that's why I say this. The real value functions on the real line, the continuous real value functions is embeddable in our topos as this R5. So now we can talk about approximating the derivative. So we say that one real value, interval value function of time y approximates the derivative of some real value continuous function if, and this may look both familiar and weird, x at time r2 minus x at time r1 is divided by r2 minus 1 is approximated by y. So if for all r1, r2 that holds, then you would say that y approximates the derivative. And what that means is that you've got your function, you say that you want to know if y approximates the derivative at every point in this thing, but let's just look at one point. You say for all rs, the secant line from r to s is approximate. So this, let's say the secant line has slope 0.5, then y is an interval value function that surrounds 0.5. So y is an interval value function of time, and is constantly surrounding the derivative of x. And this forms a directed family, the y's that approximate the derivatives, so we can take the kind of limit of, or soup of this directed family and define x dot to be that. So it kind of looks familiar, and it does work, because internally it's linear, you can tell the derivative is linear, and derivative of time is 1, and it satisfies the product rule, and you can prove those things. And externally, you can check that it really is the derivative when the derivative exists. But it even makes sense when the derivative doesn't exist. For example, with absolute value function, if you try to take the absolute value of this, you get an interval value, the derivative of this, you get an interval value function that's -1, that's just equal to -1 when time is less than 0. It's equal to 1 when time is greater than 0, but it's the interval -1 to 1. So this is actually a real picture of the derivative. It's not, I didn't mess up by forgetting to put an open circle here or something. This is the interval that you get for the derivative. So you all, for every continuous function, you do get an interval value derivative. It's the limit of a certain directed family in Sheaves, in an internal locale somehow in the Sheaves. Right. Yeah, so the IR that I wrote down is an internal domain, and you can take soups of directed families. Okay. So now differential equations just become logical expressions. I define x dot internally, x double dot internally. If a and b, if I have a function, if I have a differential equation that looks like this, that's just an equality of real numbers or variable real numbers in the topos. So maybe a and b are continuous functions. In fact, everything's continuous functions in time. Maybe a and b are constant, but usually everything in here is continuous function in time. I mean, you can talk about groups in any topos. In this topos, if you talk about a group object, it's a group that's changing in time. If you talk about a database, it's a database changing in time, like a temporal database. You can't not have something timey. You can make something constant in time, but that's like an extra condition. So anyway, you have all these various.
Do you need any differentiability hypothesis, or is everything at the perfect time going to be?
Right. So for us, differentiable means that the intervals are always 0 to 1. Because we always get a derivative. Everything's differentiable. What we call it, classically differentiable in the usual sense, that this interval is again 0 length for all time. And you're right, to write these down, that's better be a function of intervals, unless I've already proven that x and x prime are differentiable. But you can write this down, and you can, as long as that has the appropriate type, meaning it takes in interval reals, or you've proven already that these are differentiable, and this will make sense directly in one. Right, so I can combine this with and, or, not, for all, exists, etc. And I can combine it with other properties. And now I'll say how to look in this national airspace example in very simplified cases. So the real problem is safe separation for pairs of airplanes, where you have components like radars and pilots and thrusters and actuators, and you have discrete signals and continuous differential equations and delays. But what we thought, to prove the safety of this is millions of man hours, person hours of work. In our simplification, we just want to make sure we can use these various systems and put them together. So we just have one plane trying to achieve a safe altitude, which doesn't sound very hard, but we have one radar, one pilot, one thruster, and we're going to be using the same behavior types as up here. Discrete, like stochastically, signals that kind of come at stochastic moments, continuous differential equations, and delay, to show that we can understand behaviors over time. And let's try to prove something. So here are the variables we'll use: a term t of type time, or variable t of type time, two tcast commands, one that the tcast is going to send, and one that the pilot is going to send. And these are going to either be stay level or go up, stay level or climb. A is going to be a variable real, which means it's a real that's changing in time. And safe, margin, delay, and rate will be rational numbers. So T is like a timeline, A is the altitude, continuously changing. TCAS commands from the TCAS and the pilot are occurring at whenever they want, at discrete moments of time. And these are four rational numbers.
Why are they rational?
Because, I don't know, think we real. There's so many reals around. There's the constant real. So it turns out if you write down the real numbers object in this topos, you get a constant family, constant sheet. Whereas the variable reals allow you to look at things like this. There's so many reals floating around in dimensional arrays. So the first rule I need to prove safe separation is that the margin is greater than 0, and that the altitude of the plane is always greater than 0. And what's the margin about? The margin is just some number that I'm going to make a rule that says if my altitude is bigger than safe plus margin, let's say safe altitude is 10,000 feet and the margin is 100 feet. So if I'm more than 10,000 plus 100, you can stay level. And if I'm less than 10,000 plus 100, then climb. I just need to get higher than 10,000 to win, to be safe. And then I have a differential equation kind of thing that says that if the TCAS barks level, then, or if the pilot says level, then the altitude of the plane is not changing. The derivative is equal to 0. Whereas if the pilot says climb, then the derivative equals 3. And there's some longer logical condition I'm not going to write down that says that the TCAS, when you delay it by del seconds, is doing the same thing as the pilot. And from these, I'm not going to prove it to you, but you can write down a proof that for all time, if you witnessed or started your stopwatch at 0, then when time is bigger than delay plus safe over rate, so the delay of the pilot plus safe divided by rate, then the altitude of the plane is safe. So you can prove this property from these differential equations and whatever else is here. Okay, so that's pretty much it. I'm just going to summarize the thing that's said so that I'll be on the screen if you want to ask questions. So we're writing down a topos for integrating various systems. And the systems are characterized by what their possible behaviors are. Are they real value functions of time? Are they discrete signals? Or what are they? And B is the topos of behavior types, and a sheaf in it tells you the possible behaviors of any length of time. And we kind of considered a system like this. We integrated various conditions on the system to get to this one plane. And each component has an interface, which is kind of what you're allowed to see from outside. And you can ask questions about that interface. You can ask questions about what it's able to do. And those types of questions or things it can do are, I always satisfy this differential equation, or I always delay my input by 5 seconds, or whatever. And so this is a new temporal type theory of sheaf semantics. Thanks.
So we have time, 10 minutes for questions, and then we'll jump straight into the attending discussion. So, questions?
Yeah.
Just put that archive number back on. That's sure by very quickly.
Oh, yeah, right. Yeah.
So a few years ago I heard that there was an experimental plugin for Puck for reasoning in the internal logic of things on the site.
Oh, cool. I didn't know about that.
I know a guy who was involved in that, or at least I used to know a guy involved in that. I can't remember what it was called.
Okay.
But
Well,
presumably for each given site it can, I would guess, work out what extra axioms you can add to your type theory.
yeah, because we just write these axioms directly into the type theory as axioms. But you could start from, I don't know what a deep and shallow embedding is, but maybe somehow they're putting, we don't talk about the site itself. We kind of just start with the type theory that we, over here, as mathematicians, prove was sound. But maybe this.
I will try to find out what it's called and then get back to you.
Thanks. Yeah.
So that makes me, maybe I didn't absorb it. So do you have enough axioms in your internal, you can phrase in your internal language that you're sort of either specifying the site?
No. Right. So no.
Can you even do that? Is there a thing
I-
like that where you like take
what
all the
yeah.
everything that's true and specific unique topos and make that axioms and then have to
Yeah, so that sounds like what Jules is saying. You could write down the site in COC, and then somehow it would help you. It would tell you all the axioms in the world. Because what I said was, no, we're just going to start with one type called time and one predicate or something, and then we're going to write down 10 axioms, and then we've done, and that's the only thing you're allowed to use. And that's not the topos here. That's just a topos with a map to this topos. That's, everything is going to be sound in this topos.
do you have other models of that?
No.
So sort of
Yeah, but I guess we said we were done when we were able to prove, write down what a derivative was and prove that it satisfies product rule and stuff like that. It seemed, and get everything in here and there. We thought, okay, this is at least a stopping point for us.
It seems that you are using the internal logic of the topos. I mean, that's obviously what the tricky trial semantics applies to. You're sort of embedding that into something like COP. Is that
Yeah, so we have a type theory that's much smaller than the whole internal logic. It maps into the internal. And that is what we were planning to put. So we put that into Leiden, which is kind of a proof system. It's not that easy to work with proof assistants, at least for me. But yeah, they don't help you very much. Anyway,
right. But I think the logic is just intuitionistic logic.
Yeah.
Because there might be issues in going to something like POP, which has dependent types and so on. I mean, it's not exactly the same as the.
No, you can when you start with a type theory, you can embed it directly into the COP. Like I can write down those axioms in finite time, in a few days in COP, or in Leiden. It's not the entire internal logic of the topos. It's just a fragment of it.
But this ensures that your logic is consistent.
Right. What ensures that?
The embedding into the topos.
Yeah, the proof ensures that. Yeah.
My other question was going to be, so you've sort of, you can include the sort of differential equation stuff in the languages you showed, but I mean, for things like, showing the existence of a solution.
Yeah, right.
What goes into that?
Yeah, right. So this is, we call it a Big Tent framework. What that means is if you have logic of differential equations, as it usually is, if you, or what they do in formal methods is what's called model checking. So if you have a model checker, which means you have some linear temporal logic statements and some
you want to know if they're valid or something. This thing will create either a proof or a counterexample of these statements, and we'll do it in some amount of time. If you have one of those, you should definitely use it and not try to prove it in here. This is kind of a big tent framework, and what I mean by that is once you've proven something about differential equations, like the existence of a solution or something about temporal logic, you can embed those proofs into here, and those proofs will still be correct in here. But now you can combine them. You don't want to work. This is kind of as a last step for putting things together.
Right, but then you might need some hypothesis there because you might have been using classical logic.
Right.
Which is typically the case with those kind of temporal logics, and also, I guess, with just using classical analysis proofs of existence.
Yeah, those analysis proofs shouldn't be a. I mean, the non-classicality of this logic, which means, so classical means that you can guarantee that P or not P holds. That's kind of the main one. This is not true because for us, a P is not a true or false, it's a when. So it's one of these Lipschitz curves that say which intervals is this true over. And not P not P will kind of kill all the information except, I don't know how to say it. It kills a lot of information. But the kind of information it kills shouldn't be a problem for differential equations, because what this is about in terms of differential equation is trajectories. And it's not the only thing that, anything that's at a single point, it will still be Boolean. I don't know how to say this. If a trajectory, I don't know if I can do this justice, but if a trajectory doesn't, it's not the case that it either does or doesn't satisfy a property. It's satisfied at certain points, certain areas. So for example, okay, here's an example. You have some space and you have some area in that space, and you've got a differential equation, which is some vector field on the space, and you've got a trajectory of that vector field. Then for some periods of time it's satisfying, and for other periods it's not satisfying. But it's not the case that for arbitrary trajectories, either they completely satisfy or they don't satisfy. I don't know. I don't know how to say it.
There might be some very interesting kind of meta theorem that says you can carry over some chunk of classical analysis into here because of those considerations. But one might need to formulate that. Yeah, interesting.
Do you want to go first? Okay. This is possibly not a question I can expect you to answer, but I wonder about the relative practicality of doing differential equations this way versus using synthetic differential geometry, where instead of defining an object of real numbers, you define an object of, I guess, they're dual real numbers. So an object of numbers of the form x plus dx.
Yeah. So I guess in that context, and I don't know it very well, but everything is assumed to have to be smooth in some sense. And we want to work with things that are not smooth, like labeled transition systems that are making what are called hybrid systems that are able to take in information packets and do non-smooth behavior. So that's, we decided not to go with synthetic differential geometry because it bakes in a lot more information and we kind of wanted less information. But in terms of where you should solve differential equations, if that's all you're going to do, maybe it's much better to do that.
So this is, I guess following on a bit of what Samson said, also about soundness. So if you look at the way a proof assistant like Isabel uses next kind of tools, it's relatively young but sound. But what it'll do is call out Z3 or something like that. Z3 will do some incredibly clever stuff that it knows nothing about. So it's basically a black box, kind of like these wall checkers. And it will come back and say, I came up with a proof. Here's the lemmas that I needed. And just by picking the 10 lemmas that it needed, then Isabel's really dumb theorem prover on the inside can actually reconstruct the proof in the way that it knows is sound. So maybe your sort of big tent architecture can use some sort of idea.
Right, yeah.
Get the tool to give you just enough information that now you know how to
Yeah, that'd be great. Yeah. That'd be cool.
I have a question.
Yeah.
So there's been some recent work on sort of formal verification of cytophysical systems about, for example, Alessandro Lattes who uses Bayesian networks to do graph estimation in the formal verification context. And talk about big tents. Have you guys thought about incorporating probabilistic or even causal notions into this process?
Yeah, so we definitely want to get probability. So if you have some kind of internal locale, or you have some, you're looking at trajectories through time, and you're looking at open subsets of that. So you give some notion of what an open subset of trajectories is. Then you could try to give a probability measure to those open subsets, and maybe try to recover stochastic processes or Markov processes using probability measure. The problem is that probability is pretty classical, like sigma, alpha, things like that, and complements. We don't want that, so we're thinking of using what's called probabilistic power domains, but it's for valuations where you have a slightly different logic of probability, but it's similar. I think it's very close to the same in individual context.
Valuation doesn't like valuation algorithms.
Not in terms of like abstract algebra, but you have some kind of measure mu satisfying some properties like mu of p plus mu of q plus mu of or minus mu of p and q. So this is like an inclusion-exclusion formula equals mu of p or q. So the probability measure of p plus probability measure of q minus probability measure of their intersection equals the probability measure of their union. You write down, say, 4 axioms like that, and they tend to get pretty close to classical probability theory. And that works a lot better in a physics setting.
One more question.
Just a comment. Hyperbole, as discrete dynamical systems, I think it's very closely related to this.
You said someone's name?
I'll tell you the name hyperbole.
Okay. Okay. Has done discrete dynamical systems in some way that's compatible with this.
Yes.
Okay.
Very good.
Okay, that would be cool to talk about.
I guess before we start the plenary discussion, are we going in banking data?